Good day, everyone. So, today we shall be looking at another interesting topic, electromagnetic induction. In our previous class, we talked about electromagnetic field, and we were able to say that it is a combination of electric field and magnetic field. And we could observe in that teaching that when a current flows through a conductor, it generates magnetic field. But this time around, we are diving into this electromagnetic field in a different dimension, and that is electromagnetic induction. What can be induced when there is electromagnetic field, or how does it occur? Okay, without much ado, let's dive in. All right, now when we talk about electromagnetic induction, it's simply defined as the process by which a changing magnetic field produces an electric current in a conductor. You'll be surprised that when you get when you get a magnet, look at this magnet now. You get a magnet and you take that magnet through. You take that magnet through a conductor like this solenoid. Okay. Now, what you will observe is that there will be electricity induced. You could see in this case now, as you are moving this magnet into this conductor, you will find that electric current has been induced into it. And this galvanometer is just an instrument to dictate the flow of the current. Now, this current that has been induced is called the induced current. So whenever there is a changing magnetic field as a result of the change in motion of the magnet in a conductor, it induces electric current to that conductor, and that electric current is known as induced current. Now, this induced current, sometimes we call it EMF. This induced EMF or current depends on three things: the speed of the magnet. If you move the magnet faster, then you will have more current induced into this conductor called the solenoid. Another thing is the number of turns of the conductor. Now, if we have more turns in this conductor, then the amount of current that will be induced will be increased as well. And the third thing is the presence of soft iron core inside the core. Very important. The soft iron core, which is a magnetic material, also help in inducing more current into this coil. So these three factors affect the quantity of current induced into the conductor. All right. Now, the direction of the magnet tells us the direction of the current induced. Now, if the magnet is moving from left to right that you're seeing, now the current induced will move in the reverse direction. You can see in this case now, it's moving from left to right. Now the current is moving right to left. But if it turns the other way around, the current will move left to right. So those are the things about electromagnetic induction, a process where a changing magnetic field produces an electric current in a conductor. Okay, now there are two laws that guide this induction of current into the conductor. And the first law is known as the Faraday's law of electromagnetic induction, and the second law is Lenz's law of electromagnetic induction. And how did this law affect the induction of current when there's a changing magnetic field? Let's consider the law of Faraday. Faraday noticed that, just like we have considered the factor that affects the amount of current, he noticed that the higher the speed of the magnet, the more the conductor that is induced into, the more the current that is induced into the conductor. Now, in his law, he states that whenever there is a change in the magnetic line of force, okay, the strength of the induced current is proportional to the rate of change of the flux linked with the circuit. Magnetic flux is the magnetic field you are talking about. So the rate of change of the magnetic field is proportional to the induced EMF or current. That's the law. So in mathematical form, the first change in flux is leads to greater induced EMF. Now, if there is no change in flux, there cannot be induced EMF. So if there is no movement of magnet, you cannot have induced EMF or current into the conductor. So that's what the law of Faraday is stating. Now let's consider Lenz's law on this electromagnetic induction as well. Lenz's law, in his own observation, is still based on what we have also. His own is that he's interested in the direction of the induced current. He said that in his law that the induced EMF or current is in a direction such as to oppose the motion changing or producing it. So the induced EMF is in a direction to oppose the motion or change producing the motion. That means as this motion of the magnet is moving toward the right, the induced EMF move toward the left to oppose the motion. So let's look at after the what? The direction of the induced EMF or current. Now let's talk about another device known as induction coil. Of course, we've talked about induced current, so it's not far from it. The induction coil is just like this. This is a sample of it. It consists of turns both at the right hand side and the left hand side. Okay, now it's a device that is capable of producing a very high EMF by electromagnetic induction. And how does it work? Now, when you connect a battery that has a low EMF to an induction coil in this place, as shown here, now the amount of EMF it will produce will be higher, and that's because the number of turns at the right hand side is higher. Okay, and then the magnetic core also generates magnetic field that induces more EMF into the coil. So that is how the induction coil works. One, there is battery connected to it. The battery supply current, and when you supply current to this, the coil itself, the coil itself generates a magnetic field, and the magnetic field is being enhanced by the magnetic coil. We supply more current or voltage or EMF to the other side of the coil, and then we have higher voltage produced. Okay, let's now talk about another aspect of this magnetic field, electromagnetic field induction. Now, there's another observation that the scientists have noticed with the load guiding it. And what is it? When we have said, when you in the previous one, we are talking about moving a magnet. In this case, moving a magnet, okay, into a conductor, and then electric current induced. But this time around, we are now looking at moving a conductor now this time around into the magnetic field. The magnetic field is stationed, and then the conductor is moved into it. Okay, so when that happens, when there is a movement of a conductor into the magnetic field, what is being observed? There is still an induction of current. There is still induced current, and the Fleming's right angle will help us to understand it better. In its rule, it states that if the thumb, the forefinger, the middle finger, as shown here, this is the thumb here, this is the forefinger, the middle finger. Now, if the three fingers are held mutually at right angle to one another, as shown here, in his law, or in his rule rather, it states that the thumb represents the motion of the conductor that is being passed through the field of the magnet, and then the forefinger represents the direction of the magnetic field, as shown in this place, and then the middle finger now represents the direction of the induced current. So Fleming's right angle helps us to know that the induced current, the direction of the conductor, and the magnetic field are all at right angle to each other, and because of that, we are able to determine their direction using Fleming's right hand rule. So it's very simple, just for us to have a better understanding that these three phenomena are at right angle to each other, even though we have said it before. Fleming's right angle is just giving us a clearer understanding of their direction. All right. Remember, we also have Fleming left hand rule. Fleming left hand rule is made for a situation where electricity is connected to the conductor and then it generates its own magnetic field. Okay, but in this case, this time around, electricity is not connected to the conductor, rather there is an induced current into the conductor. So let's just be able to differentiate between the Fleming left hand rule and the Fleming right hand rule. Moving on, let's now talk about a very important machine known as generator. A generator is a machine that converts mechanical energy into electrical energy. Okay, and it's of two types. We have the AC and the DC generator. Of course, the word AC means alternating current, DC means direct current. Now, this generator also makes use of electromagnetic induction. Of course, we have said this is a typical diagram of AC generator. It has a magnet, horseshoe magnet having a north and a south pole. Now, this is the armature, what we have been referring to as coil. Now, this armature is moving, is able to move because of what? Of the presence of the magnet. All right. When you move the armature mechanically within the magnetic field, what happens is that there will be what? Induction of electric current into it. And that current that is being induced into it is now what supply to this bulb here. So that's why in our various home we have to drag our generator. Dragging it is what? Is to make the armature, which is the coil, to move. And when it moves through the magnetic field, electricity or electric current is induced into it, which is sent into our loads like our bulb, our TV. Now, what it automatically supply is AC current, alternating current. It supply alternating current when this happen. Now, these two ring here, they are called slip ring. The slip ring allow the current to keep flowing in that alternating way. You see the arrow pointing left and right. That shows that it's going from right to left. That's how alternating current works. And this alternating current is also proving towards Lenz's law that says that the current induced is always in your opposition to the what? To the motion causing it. All right. So now, how do we now change AC generator to DC generator? Very simple. In AC generator, we have the armature, we have the slip ring, we have the brush that keep cleaning the slip ring. But in DC, if we want to change AC to DC, what we need to do is to replace these two slip rings with split rings. The split ring is the one that helps us to what? To change the AC current to DC current. So that is just the major difference between AC generator and DC generator. In AC generator, we have two slip rings. From here you can see two slip rings. While in DC generator, we have just one split ring, or what we call the commutator. The split ring in this is also known as the commutator. It helps to change the AC to DC current. So the commutator is just a current reverser, maintaining the direction of the current in one direction. All right. So that is another. So we have just seen one area of application of what? Electromagnetic induction. Okay. Now let's talk about another aspect. Another device, very important, a transformer. A transformer, we have all heard the word transformer, or says most time we say, oh, the transformer in our home is fault, in our area is faulty. Now it's a device that changing the side of AC voltage. It's a device that is capable of changing AC voltage to high or low. So it's either it can increase the voltage of an AC or decrease the voltage of an AC voltage. All right. Now, when it is increasing the voltage of an AC, that type of transformer is called step-up transformer. But when it is decreasing it, it's called step-down transformer. And how do you know step-up transformer? A transformer, first of all, has its own components. You could see here, this place is known as the primary circuit here, the red sign here. The primary circuit is the one that is connected to the main supply of AC voltage. Now, when it's connected to it, it now increases. How does it do that? It goes to the other side of the circuit, called the secondary circuit. You could see the blue tones. Now you could see that the blue tones is more than the red tones. This shows that this is what a step-up transformer, because the primary circuit here. So in this case, this blue side is the primary. I label here as primary. Okay, the primary voltage here has higher turns than the secondary voltage. Now this shows that this is a step down transformer, not step up, because the primary voltage has more turns than the secondary voltage. So the primary voltage is the one that gets the external supply, okay, and then by the time it's sent into the secondary, because the secondary turns is lesser, it sends the lesser voltage. So if from the primary you are getting 50 volt, because the turn is higher, we have 50 volt. When it's coming to the secondary, because it has a lesser turn, you're going to be supplying something like 20 volt or 10 volt. That's how you know. That's why it is called a step down transformer. But on the other hand, if this number of turns in the primary circuit is lesser and the one on the secondary is higher, then it is called the step up transformer. Okay, and this thing at the center is known as what? The magnetic core. Is the one that help in enhancing the magnetic field that now induce more voltage, either high or low. Okay, so having said that, let's now talk about energy loss in transformer. As transformer is working, it loses some energy, and this energy are lost through 4 different ways. Number one, through eddy current. The eddy current is a loop of current induced within the conductor, that means within the coil now, due to what? Changing field in the conductor. Now the eddy current, remember that whenever current is passed through a conductor, it generates its magnetic field. That magnetic field now makes the coil to still have an induced current. This induced current is known as the eddy current, and it just get wasted because it's not going to be in use. So this is one way that energy is lost, through eddy current. Another way you lose energy in a transformer is through hysteresis loss. This one is wasted energy due to reversing the magnetization of the core. Okay, now this hysteresis loss happens to be loss of energy because of what? Change in the magnetic field of this core. All right, another way you can lose energy in a transformer is through heat. As this coil are getting hot, they generate their own heat, and in this way energy is also lost. And the last way you can lose energy in a transformer is through leakage of magnetic flux. When the magnetic flux are being lost, then are being leaked rather, then you also have loss of energy. Now, how do we reduce this loss of energy in transformer? For the one of eddy current, it can be reduced by laminating the magnetic core. Okay, for the one of hysteresis loss, it can be reduced by the use of special alloy in the core of the primary coil. Use special alloy in the coil. For the one of heat loss, it can be reduced by using a low resistance coil. And for the one of leakage of magnetic flux, it can be reduced by efficient coil design. When it is efficiently designed, it will not be leaking its magnetic flux. Okay, now there are some formulas we use in calculating some quantities in transformer, and I just have a few of them here. The first one is the ratio of secondary voltage to primary voltage equals to the number of turns in secondary voltage in the secondary circuit rather, to that of the primary circuit. Another one is that the power in the secondary circuit is equal to the power in the primary circuit. In that case, the primary circuit formula is current in the secondary circuit multiplied by voltage in the secondary circuit. While the power in the primary circuit is current in the primary circuit multiplied by voltage in the primary circuit. So we have two equations here. Now if you equate equation 1 and 2, we'll be having this formula: IP over IS equal to ES over EP, which is equal to NS over EP, depending on the way the question is being sent. Sometimes it can be hard to find the efficiency of the transformer. Efficiency by formula is ratio of the power in the secondary coil to that of power in the primary coil multiplied by 100%. Okay, so now let's go on to see an example on this. Look at this question. It said, find the turns ratio in a transformer which delivers a voltage of 120 volts in the secondary coil from a primary voltage of 60 volts. So in this question, we have to find the turns ratio. That the turns ratio is number of turns in secondary coil over number of turns in primary coil. That's the ratio. So that's the unknown. So Ns over Np is equal to unknown. But we are given voltage in the secondary circuit, which is 120. So we have our Ex, the E represents the voltage, equal to 120 volt. We are also given voltage in the primary circuit, which is our Ep, and that is our 60 volt. Now, using the formula Es over Ep equals to Ns over Np, and then making Ns over Np our subject of the formula, we'll be having Ns over Np to be equal to 120 over 60, which will give us 2. So the ratio of number of turns in secondary circuit to that of number of turns in primary circuit equals to 2. Okay. Another example, it said a transformer has 500 turns in the primary coil, that is Np, and 300 turns in the secondary coil, that is Ns. If the primary coil is connected to a 220 volt, that means our Ep is 220 volt. What voltage will be obtained from the secondary coil? So we are looking for Es. And what type of transformer is this? Of course, let's quickly answer the last question. This transformer, because the number of turns in primary coil is more than the one of secondary coil, it is stepped down. Okay, whenever the one in the secondary coil is lesser than the one in primary coil, that is a step down transformer. Now let's go answering the question. Now, what voltage will be obtained from the secondary coil? That is Ex. So our Ns is 300, Np is 500 turns, Es is unknown, Ep is 22 volt. So using this formula and substitute the value of each of them here, our Es will be 132 volt. Okay, so let's take one more question and then we move on. A transformer supplies 15 volt. In other words, that is our Ep this time around is 15 volt. Sorry, if transformer supply 15 volt, that means the secondary voltage now, because it's the one that's receiving it now, is 15 volt. That is Es is 15 volt from a 220 volt main. So because it's coming from a source, so that source is our Ep, and that is our Ep is 220 volt as written here. So if the transformer takes 0.7 ampere, that's our Ip. Now the current that is coming from the primary circuit, so our Ip is 0.7 ampere from the main when used to light 3 lamps. These lamps are the ones that are in the secondary circuit receiving it now. So these 3 lamps are connected in parallel. Whenever lamps are connected in parallel, we know that they consume different power but the same voltage. They consume different power, they consume different current but the same voltage whenever they're in parallel. Now the rate of these lamps are 15 volt and 40 watt. Okay, so of course in that question we know that in the question we know that this our electric, this one is not part of it. The number of turn is not given here, so we have no business with this. All right, so in this case now we are giving our secondary voltage to be 15 volt. In this case, this supplies, and our primary voltage is 220 volt, like I said earlier. Then we are giving the secondary power to be 3 lamps, that's 3 times 40 watt, which is the power now. So 40 watt for each of them times 3 of them. So the total power in the secondary is now 120 watts. Then our primary power, remember our power formula is I times E. So that will be we are not giving this as well. So this is okay. So we are giving our if the transformer takes 0.7 ampere, so that our I now is 0.7, okay, from 220. So this is given to be 220 volt, and multiplying it together we have 154 watts, and then dividing it by 1000, it will be 0.14 kilowatt. We are dividing it by 1000 because we want to convert it to kilowatt. All right, now we have to calculate the efficiency of the transformer. By formula, efficiency is power in the secondary voltage divided by power in the primary voltage times 100%. Now we have obtained our Px to be 120 and our Pp to be 154, okay, times 100. Now when you simplify this, you'll be having the efficiency to be 77.9%. all right, now the second question says we should calculate the cost of using it for 24 hours at 30 kobo per kilowatt hour. This is the reason why we converted this 154 to kilowatt hour, because energy consumed in 24 hours will be power, the primary power multiplied by 24 hours, and that is 3.696 kilowatt hour. So that is energy consumed in 24 hours. Now, if the cost of energy consumed is 30 kobo per kilowatt hour, then for 3.696, how much will be consumed? It will just be 3.696 times 30 kobo, and that is 110.88 kobo, which is 1 naira, 1.1 naira. All right. So having said that, let's talk about power transmission. Power transmission. We all use electricity in our various homes, but let me let you know that today it is not the amount of power being transmitted from the source that we get that it need to step down this voltage. So transmitting power at high current can also lead to loss of energy. If you transmit this power from the main source, before you get to us, it will have loss of energy. And to avoid that, there is need to transmit at low current but with high voltage. This is known as high tension transmission. When you are transmitting high voltage but low current, it's not high tension transmission. And for us to now step this high voltage, we now use a step down transformer. Okay, you can see it here. So this is the high voltage transmission. The transformer helps us step it down and extend it to all to our local houses. So this is how the power transmission works. And this is where we shall be drawing the curtain for today. So they are coming your way again. Thank you for listening.